Hello everyone, it's good to have you back. We're going to talk about confidence intervals, and in this particular section we're going to talk about confidence intervals of the mean when we know the standard deviation, and that's very important. One thing that will be even more important than before is knowing what the prerequisites are. In this case, we're talking about the mean, and we know the standard deviation for not the sample, but for the population. And with that said, let's move on. Here are the four sections in chapter 4. We're going to cover at least the two. I'm going to make videos for all four though. And if you do one or two of the extra ones, you'll get extra credit for it too. In fact, if you do enough extra ones, I'll probably exempt you from the final exam. So this is what we're going to do. And if you relax, you'll find that most of these pieces are pretty easy, but take good notes. Pay attention to what I emphasize. All right, first of all, we're going to look for a point estimate. And that just means, what are we looking for? Well, what's the closest thing that's going to give us an idea of what the real number is? We'll get back to that. Margin of error, how far off can we afford to be? Second, how do you interpret those confidence intervals? Because this point estimate says there's one number that's going to give you an idea about the mean or whatever it is you're interested in. However, it's unlikely to hit it right on the button. It's much more intuitive to say, well, we think that particular parameter is between this number and this number. And that's what we're going to talk about in this beginning section. And third, and maybe easiest of all, although the formula doesn't look great at the beginning, remember, add it to your notes because you want to use it when you get to the test time too. So we're going to find out what the minimum sample size is. How many people do you have to talk to? Or how many 2x4s do you have to measure so that you get the correct size of the confidence interval you want? Okay, we talked about point estimate, and the starting point here is you're interested in the population parameter. For example, it might be the weight, the average weight for whatever you're interested in. Now, the point estimate means there's one number that maybe you can find that'll give you an idea what this really is. Although this population parameter, we don't know. What we can do is take a sample and using that sample, get an estimate. This estimate will say, you know something? I think the population parameter is probably pretty close to this estimate I just got. Second, what about that point estimate? What is the best point estimate we can create? Well, you might be surprised, you might not be surprised, that if this is what you're interested in, the population mean, the best point estimate, the most unbiased one, is X bar, which is the sample mean. Remember, the sample mean is the sum of all those X's divided by how many of those values you have. So here's one you might want to keep in mind for estimating a population parameter. For the mean, if this is what you're interested in, the mean, this is a good point estimate. get this, and in all likelihood, you're going to get fairly close to the real mean. Okay, now, I think I've said this before. Again, get your pause button ready. Usually the space bar. And let's see where, there we go. However you pause your video, this one, make sure you're ready to do that, because when you get to some of these exercises, even if you can't do it, hit the pause button, give it a try. It doesn't matter if you mess up. I'm not watching, no one else is watching. See if you can get the answer. If you can't, you can always go back. You're going to learn something by actually trying it, and you're going to fine-tune whatever you did know. So in this one, notice that we've got a bunch of data, a whole table full of data, and this is a random sample of 40 student athletes. We want to get an idea of what is the mean of number of hours they spend on athletic activities. Now, we're talking about all student athletes, so we want the population mean. However, we had to pick 40 because maybe even at USC Upstate, maybe there are a couple hundred of them, and you do have other classes to work for, right? So you might pick 40 because 40 is a doable exercise. 400, that would take a lot of your time. You might miss a few meals. You don't want to do that. So we get these 40 that you see down here, and we're going to use those to find a point estimate, in other words, a guesstimate of what this mean really is. We don't know the mean, remember, but we're going to see if we can get an idea of what it might be. You might eyeball these and say it's probably in the high teens or low 20s, but that's subjective, right? So we want something we can have a little bit more faith in, or a little bit more confidence. So remember, before you hit pause, you'll probably be putting these in list 1. Remember, stat, edit is how you get there. Put those into L1 and you'll be ready to go. I dare you to try it. If you don't make it, that's no problem. But I think you can do it. All right, you're back. So, sample mean of the data is 19.925. Now remember, you could get that by stat, calculate, submenu, and go to the first one in that list, one variable stats. You're going to need to tell it you got your items in L1, and that's most of what you're going to need. We'll narrow this down a little bit later, but that's a good start for you. We've done that in chapter 2, so you might be able to do this. So what we've got is the point estimate. 19.925 hours is an approximation of what the real mean is. We don't know what this is, but this is an estimate. We hope it's close, and there's a chance it might not be, but if you get a good sample, it's likely that this is going to give you a pretty good idea of what that mean is. Now, that point estimate is sort of iffy. It might be too high, it might be too low, Most likely is one of the two. There's almost no chance of getting it exactly, but we wouldn't know anyway. We don't know what the population parameter is. So we wouldn't know if we hit on the button or not. So instead, what we're going to do is, instead of a point estimate, we're going to have an interval estimate. Before finding a margin of error, you have to first decide how confident do you need to be. There's a starting point. Before you do any calculations, before calculating, decide on your confidence. How important is it that you get pretty close to that population mean you're interested in? So I talked about the level of confidence. We represent that by a C. It's a positive number, and it's between 0 and 1. And what this represents is the probability that the interval estimate, instead of a point estimate, so we're going to have an interval like this, and let's say it was between 6 and 19. So this would be an interval, and this would mean that we think that our mean is somewhere in there. We don't know for sure though. Either it is or it isn't, but that's our best guess. It's an interval estimate. Now, this confidence is quite often described as a percent. For example, you might say C equals 90%. You want to be 90% sure that the mean probably is in that interval you found. Or maybe you want it 95% because it's much more important. Or 99%. If it's a life and death matter, 99% might be where you want to go. Usually, you work with 95%. And since your calculator really doesn't care for seeing these percentages, make sure that if C is 90%, in your box of information, put 0.90. Make it as a decimal, not as a percent. Now that means you're going to be 90% sure if you did that estimation process a lot of times, then 90% of the time that mu will be somewhere in the interval. Sometimes you'll get that interval and mu wasn't in there. You'll never know, but that's the chance you take. Now let's get down to a little bit more of the nitty-gritty on this one. Critical values. This is what separates sample statistics that are probable from those that are improbable or very unusual. What is a typical result? Are you likely to see it, or are you unlikely to see it? Critical values are those cutoff points. So you might, here's a sneak peek. Here's one of those curves we kept using, and we're going to use even more now. Remember the mean, if we know it, is in there. And the critical values will be on the two ends. This will be the critical value, we'll call it X, C lower, X, C for critical upper. You don't have to do that. You can just put it C, X, what I do is I use XC, and maybe XC for this one and minus XC for this one, because they'll have the same magnitude, they'll just have different signs. And this is a cutoff point. If we find the value, suppose we do our statistical testing and we find X bar, our point estimate, is 19. Where is that 19? Is it close to the middle? Or maybe it's out here. And if it's out beyond your critical points, that's not good. That means it's a really unusual value. Here's a picture. We're talking about C being 90%. Remember, you'd write that as 0.90 for the calculator. It likes that. Now, for confidence intervals, that C is right in the middle. All of this represents the area that's represented by C. Now, C isn't 100%. There are always some areas on the right and on the left with what's left over from 100%. So in this case, we've got C is 0.90, and that means what's in the two ends, the right and the left tails, is what's left over. 100% minus 90%. Another way of putting that is 1.00 minus 0.90. And there is what we're going to have in the yellow regions, the far left and the far right. Now, since the normal curve, which we are usually working with, is symmetric, then this part right here, the 0.10, is going to be split in half, part on the left, part on the right. So after we get that 1 minus C, we divide it by 2. So each of those tails has an area of 0.05. Once you've got the 0.05, what the area is in one of those tails, you want to find the critical points, the critical values. How do you do that? Well, not too hard, because first of all, we've got lots of scratching here. So what I'm going to do temporarily is I'm going to change the color of this. We'll make it blue, perhaps. Okay, so here we are. Testing. There. Got some blue scratching. Now, how do you get those critical values? Well, you've already done something very similar to this. First of all, you're going to draw a picture for yourself of that normal curve. Notice we're talking about Z values, so it's a standard normal curve. And you want to find out where this critical point is. Once you've got that one, then you know that this one is the same, but on the negative side. So how do you get that? I'm going to clear something out. Let's see. It's tricky here. I'm going to just, there we go. I'm going to get rid of that. Oops. Here we go. All right. So I need to clear that out, and I'll put the pen back in order. There we go. All right. Now, how do we get those critical values? Well, let's work with one, and then the other one will be automatic. So what we want, where's my cursor there? What we want is one of those critical values. We'll get the one on the right, and then we'll know what the one on the left is. Well, it's very simple once you get this done a couple of times. To get that value, we're going to use the inverse norm function. Remember that from the last chapter. Go to second vars, which gives you the distribution menu, and this is option number 3 on that menu. Now you need your picture, and we've got the picture over here. We want to find out what this number is. Well, inverse normal says, okay, what area are we talking about? Well, let's look at this. For this z value, and I'm going to use the left side here because this will work for TI-83s and 84s and everything. For this value right here, the calculator is going to be looking for the area to the left of it. Now, if this part right here is 0.05, that means this part is 0.95 from negative infinity all the way up to this critical point. So to get z sub c, or one of the critical points, you're going to put 0.95. That's the area up to that critical point. Now we're talking about z values, and you might remember you put 0 on 1 because z values are standard deviations, and it's the special one where we have 0 for mean and 1 for standard deviation. Put those in your calculator, and this is what you'll get. Hooray! And once you have that, you have the other one. Just change the sign, and you've got the other critical value. So remember, if the level of confidence is 90%, we're 90% confident the interval that we create will have the mu inside it. And remember also, the one I just went over, to get one of those critical values, we use inverse norm, put in the area, the left area, 0 and 1, and that'll give you the right critical point. And the other one will just be the negative of that. So there's our picture. There's 90%, which is for confidence intervals. It's always exactly in the center. To get how much is in each one of those tails, you take the c, subtract it from 1. In this case, it's 1 minus 0.9 or 0.10. But that's both tails put together. For each tail, we'll have to take half of that. So we'll have 0.10, which is in both tails put together. Divide that by 2, and each tail will have 0.05 area. No units on that, by the way. And there's a good picture. And you've got how to get that z value, or how to get that critical value or values. In this case, 1.645. Now, if you use your calculator, of course, you're going to get an even more precise value, which is an advantage using the calculator over using the tables that people used to use. The tables only gave me 3 or 4 decimal places. The calculator gives me 7, 8 places, much more than I need. Next, sampling error. We haven't mentioned this before. That means when you got your point estimate, in this case, like X bar, how far off is it from the real thing? Well, the real thing is mu, but we don't know what it is. But to find out how far off it is, the difference is the X bar that we got minus the real number. The catch is we don't know what mu is. So even though we know there's a sampling error, we don't know how much it is. And on top of that, as you go from one sample to another, you're going to get different means. They probably will be close to mu, but they are likely to be different. Okay, what's the margin of error? The maximum error of estimate, or error tolerance. Imagine you need to put a pole, wooden pole, into a hole. Now you don't want to be too small to fit into this hole. You want this hole to be about the right size so that this wooden pole will be nice and tight. If it's too small, it's going to wobble. If it's too big, you won't be able to get it in. And error tolerance means how far can I be off and still find it acceptable. That's the margin of error. We call that E. It's the difference between the point estimate and the actual value of the parameter it's estimating. And here is how you get that margin of error. The margin of error is that critical value you found times standard deviation of the means. Well, that's a little bit strange. I wouldn't bother writing this down. Instead, write this down. So if you want the margin of error, what you need is to find that critical value and then multiply it by the standard deviation. Remember, in this section, we know the population standard deviation, so you can put that in. And we divide that by how big a sample you actually have, and then take the square root of that. You want this to find the margin of error, or the error tolerance. Remember though, the sample has to be random, otherwise it'll be biased. Second, it has to be either normally distributed, which you might find from your history notes, so to speak, or if it's not normally distributed, here's the other possibility. If you make your sample size 30 or more, then you don't have to worry about the original population being normally distributed. So either one of these is good. Make sure your sample is random, and either the original group or set of data is normally distributed, or your samples are 30 or more. All right, let's get back to work again. Here we've got the data from example 1, and I've copied it again down here so you can use it. You might want to, if you didn't before, you might want to hit pause now, put these numbers into L1. Now, we're working with knowing the population standard deviation. We're going to assume it's 2.4 hours. And here are all our sample data. Since we know the standard deviation, It's 2.4, and the sample is random, and we've got 40, and that's greater than or equal to 30. So we're in good shape. That means we've got a normal situation, and Z sub C makes sense. Because Z means we're working with a normal distribution. So to get E, use your calculator to get the critical value. Remember, it's the area on the left. And since you're looking for a Z critical value, we just 0 and 1 out here. And then multiply it times 2.4 and divide that by the square root of the sample size. So in this case, we'd have, if I remember right, we'd have 1.645, I think was Z sub C. Our standard deviation is known to be 2.4, and our sample size is 40. So this is going to be how we'll calculate it. Oops, we're talking about 95% confidence. Okay, so this one would work for 90% one, but that's not what we've got. So I need to clear that. Oops, where are we? All right. I'll just leave it there. Okay, so we'll restart this. We want the maximum error. So we want 95%. And if you get inverse norm, and for 95%, you'd have 0.97501. That'll give you Z sub C. In this case, 1.96. Try that on your calculator so you get practice doing it. So it'd be 1.96, 2.4 is the population standard deviation, and our sample size is 40. And you can get that answer yourself. So there's our setup. Remember, draw a picture all the time. The confidence level you have is 95. That's always in the middle. What's left? I'll say leftover. 0.05. And that's split between the two sides. So you put 0.05 divided by 2. And so each of those sides, each of those tails has an area of 0.025. And there you've got it on the picture. And there we go. I hope you paused for at least a few seconds. You should have gotten this. If you have some trouble, try it again. If you still have trouble, drop by my office, Hodge 238, or ask in class, either one. Now round it off, this is about 0.7. You could use the whole thing if you want, or you can round it off somewhat. So what does that mean? Well, this is your margin of error. So it says you're 95% confident that the margin of error is about 0.7 hours. Now, with the margin of error, now you can create a confidence interval. Remember at the beginning, we took all those numbers, found the mean, that was X bar. That's our point estimate for the population mean. And we have our error tolerance. So if we take that x bar and subtract that maximum error, and we add it to the maximum error, we'll get the confidence interval. And we expect mu to be between these. In this particular case, we're 95% confident that if we did this a lot of times, our confidence intervals would find mu right in the middle somewhere. Now remember, this probability, the 95%, is the number that we would expect if we did it a large number of times. Doing it once, you don't know. It might be a little bit off. So, steps. You want a confidence interval. And we're talking about a population mean and sigma, or the standard deviation, is known. Those three things go together. Make sure your notes include those all together. And then you can get the confidence interval for this situation. This and this and this. First of all, make sure your sample is random. Second of all, either someone tells you that the data is normally distributed in the population, or your sample is 30 or more, which will ensure that you'll have a normal distribution for your X bars. Second, what are the sample statistics? What is your sample size? What did you get for the mean? How do you get the mean? Remember, add up all the data items, divide by how many data items you have. It'll give you the sample mean. Third, find the critical value. And this is the third time you've seen this. To get that z sub c, use inverse normal. Remember, second bars, and you're going to use option number 3. And those are the numbers you need. Remember, this area is everything to the left of that critical value you're looking for. So draw that picture, because in your picture, your critical value is going to be up here. You want to know what area is all to the left of that, so you can put it in right there. And before we can go too much further, I'm going to see if I can change this back to red again, but it looks like I'm having a little bit of difficulty here. So I guess I'll just stick with blue. Okay, so with that, we just got the critical value. We already know the standard deviation. We know our sample size. All we need to do is throw those in the calculator the right way. With this margin of error, take the x bar that we got. I've got a typo here. It should be just x bar, subtract e from it, add e to it. And that is your confidence interval. Left end point, right end point. And there's your interval. C18. Make a note to myself, fix 18. There we go. All right, next. We're going back to that example again. This time we're using a 95% confidence. And you want to find the required athletic activities by all student athletes. But you don't have time to do that for all the student athletes in the conference. That would take you a lot of time. But we did already find out that from our sample mean was 19.9 hours, and our Maximum error is 0.7, our error tolerance. So there is our confidence interval, 19.2 to 20.6. Notice that 19.9 is in the middle because that's how we created our confidence interval. And that's what it looks like on the number line. 19.9, that was our sample mean. And this actual value that we're looking for, we're 95% confident is somewhere in this interval. Take note of the wording down here. Some of the wording from here on to the end is very important. So write some of these down. For confidence intervals, this would be a good way of writing it. Use those words, just replace the percent, replace the left endpoint and the right endpoint. You'll be in business. Well, of course, it won't always be athletic activities, right? Now, what's another way we could do this? Well, actually, we have used our TI-84, but you know something? We can do it even faster. Now, I showed you the other way because if you take another statistics class, maybe from the psychology department or from the business department, they might require you to do it a little bit differently. So you'll have two ways of getting these confidence intervals. This time we want a 99% confidence interval. We have a feature on that TI-84, that's why I like it so much, and that allows you to zoom through this. First of all, you have to have these numbers in one of those lists. Go to Stat, Edit, put those numbers in. Double check, maybe have someone else triple check them for you. Because if you get this 24 in as 27 or 14 or something else, then all of these numbers are going to be wasted. Here's how you do it. Now you'll want to make a note of this too. To make this much shorter, go to Stat, over to Tests on the far side, pick up number 7, which is Z interval, and we can use the Z because we know that what we've got is normally distributed. At the top, because we had all the data, remember those back here? You had all the data, not just the statistics. So if you have all the data, make sure the data is highlighted. If it's not, move it over, hit enter, and then you can switch. If you have the statistics, make sure stats is highlighted. Next, put the numbers in. You have the standard deviation, it's 2.576. You tell it what list it's in, give it the frequency, and we want a 99% confidence. Go down to calculate, and this is what you'll get. Here's another reminder of the steps that you would use to do this very quickly. And for the 99%, remember the last one, we used 95%, so the numbers are going to be a little bit different. Remember the 19.9 was in the middle. That was from your X bar. Notice it's in the middle. And plus or minus E gives you the left and the right hand tails, endpoints. It's rounded to the same number of decimal places. If you are not sure how many decimal places, just put them all in. That way you can't go wrong. Finding the significant digits is another story. If you're really interested in that, you really think you need to know that, see me, I've got some information that I can give you. Again, wording, here's your confidence level. Confidence level of what? Mean of the number of hours spent on athletic activities, and the two endpoints, 18.9 and 20.9 hours. All right, let's do one of these real quickly. First of all, you want to go through here and find the information. You're looking for the mean age, okay? You're going to have to use this as a point estimate, but what you really want is mu. However, you only have time to pick up 20 students. You'll need to make sure you pick them at random. In your sample, you got a mean of 22.9 years. So our sample is 20. The mean we got is 22.9 years. And it also says we know from previous years that the standard deviation is known to be about 1.5. So it's 1.5 years. Big item here. The population is normally distributed. Yay! That's great. Now, if it wasn't, then you'd have to make sure this was 30 or more. Keep that in mind. Very important. Otherwise, you're just getting nonsense. What you want is a 90% confidence interval. So, n equals 20. X bar is 22.9. Sigma is 1.5. That's known. And there's our critical point. The margin of error at the 90% confidence level is 0.6. And that will be in the same units. So we'll add this E value of 0.6 to the 22.9. We'll subtract it from the 22.9. There's our left hand point when we subtract, the right hand point when we add. There is our interval. Now remember, you have two different ways of doing this. I don't expect you to be able to do both, but if you can, that is a plus. Just a reminder, if you're using the TI-84, go stat, over to tests, 7, Z interval, and you can use Z because it's normally distributed. If we didn't know this, then our sample size would have to be at least 30. Once you get Z interval, you're going to get a menu, or you're going to have to put it in yourself if you've got a TI-83. So make sure stats is highlighted if you don't have the actual data. Sigma, you know, you're given that as a 1.5. This is what you got from finding the one variable stats. That's your point estimate for the mean. Your sample size is 20, and you want to be 90% confident. And there is your confidence interval. So we're 90% confident that this is between those two values. Sometimes it won't be. We won't know. But 90% of the time, it will be between those two values. That's what our confidence interval looks like on the number line. And again, good wording. You got the confidence level, you've got what you're talking about, and you've got the left and the right endpoints. This is a little bit picky, frankly. Aim to write it like this. This is another wording saying the same thing, just rearranging things a tiny bit. Saying there's a 90% probability that the actual mean is in there is incorrect. It's really splitting hairs, frankly, but once you get this interval, either mu is there or it's not. You don't know which is the case. The 90% means if you did this a lot of times, 90% of the intervals you found would have mu somewhere inside. Remember, mu, or the population mean, is a fixed number. X bar is a variable. Mu is fixed. It's either there or it's not. Don't make a big deal about this. If you accidentally think of it this way, I'm not going to be too upset. You're getting close. Now this is a picture of what this really means. To have a 90% confidence interval means you're going to do it a whole bunch of times. Now each of these lines down here represents a confidence interval that goes from here to here, from here to here. You've done it a bunch of times. Down here, we don't know what that is. Somewhere in the universe, that number exists, but we don't know what it is. We're finding a confidence interval so we can say with a certain amount of confidence that we think it's in the middle. However, notice that this is the real number we're searching for. That's what we'd like to know. Well, this first confidence interval has mu somewhere in the middle. Not directly in the middle, somewhere between the left and right endpoints. On the second one, mu is in that confidence interval. Look at the third one. Oops. This confidence interval does not include mu. The next one, mu is inside that confidence interval. Next one, it is in there. Next confidence interval, it is in there. Remember, these black dots represent the sample mean that we're using to get those confidence intervals. Next one, mu is in there. Next one, mu is in there, even if it's to the left or to the right. Mu is there, mu is in that confidence interval. So I hope this helps a little bit. And we'll wrap it up a little bit. Once you're given a confidence interval, or you have decided it, and you also know what the acceptable error is, if you know those, and remember, we know the standard deviation of the population, we can use those in this formula to find out what the minimum sample size is. Now, if you only took a sample of one, that you wouldn't be very confident, would you, that that was actually going to give you a confidence interval that was worth anything. 11, it might be pretty decent, but who knows? The bigger the sample size, the more likely we are to have a good confidence interval. Now, to figure out how many of those we need, Remember, we know the population standard deviation. From the confidence level, we know this. We know the maximum error we can accept. Put those together, and we can find out what the sample size is that we need. Don't forget, whatever number you get from this, if it's not a whole number, always round it up, never round it down, because this is the minimum number you need. If you don't know the standard deviation, then make sure that your n is at least 30 members. Your sample size is at least 3. Okay, so what are we talking about? Well, here's an example where we want to find out how many student athletes we have to be getting in our sample. We want 95% confident. Our maximum error is 0.5. So here we go. For a confidence level of 0.05, in case you're interested, to get that inverse norm. Now, what area do we need? We'll subtract the 0.95 from 1, that's 0.05, because we have to divide it by 2 because half of that is on the left and half of it is on the right. So in here, we can put one of two things. You can put 0.02501. That'll give you the left critical point. If you want the other one, or another way of doing it, to get the other one, this will give you the negative value. To get the positive value, inverse norm. If you're talking about the right one, there's 0.025 on the right side, which means on the left side, you've got 0.975. And of course, 0 and 1, because we're talking z's. Put those numbers together in your formula for the minimum sample size. And here's 88.51. So how many, if we're doing a sample of people, can we sample 88.51? No, we can't do that. Do we sample 88? No, that's not quite big enough. We always round this up if it's not a whole number to begin with. So what you really want is a sample size of 89. So make sure you have 89 student athletes for your sample. Since it actually had 40, it wasn't enough. If you want to be 95% confident, you're going to have 49 more, because 89 is the minimum number. And one last reminder, if you want to get that confidence interval quickly, then hit the stat key, go over to tests, pick number 7 for the z interval. As long as z is good, to get z, you have to have one of two things. Either your distribution is normal or your sample size is at least 30. Either of those, and you can use the z interval. Make sure you have data or stats highlighted. If you have the data, make sure data is highlighted. If you don't have the data, but you do have the stats, make sure stats is highlighted. And put in the standard deviation, put in the sample mean, the sample size, the confidence level, and hit calculate. And that's it, folks. See you again in section 2.